Okay, so thank you very much for welcoming me in this symposium. My name is Inès Jorge, and I will be presenting today an article that I wrote in the context of my thesis, which deals with the predictive prognostic of lithium-ion batteries in electric vehicles. So I'm currently doing my PhD at the INSA Strasbourg under the direction of René and the supervision of Untitled Chapter and TriRhenaTec. So today's presentation will be divided into several parts, and first of all I will briefly introduce you to the context of our work, and then I will describe the battery aging dataset on which we have based our work on, and the different remaining useful life predictive models that we have designed. So to begin with, I wanted to quickly introduce you to the vehicle project, which is a European cross-border research project that gathers many collaborators, as you can see here, mainly from France and Germany, around one goal, which is to optimize the total cost of ownership of electric vehicles. So the main areas of interest concern the improvement of lithium-ion batteries aging cycle life, and the use of variable reluctance measures. So in this context, different strategies are being led with the development of innovative hybrid storage systems, and also better energy management strategies, but also machine learning strategies to better understand the aging mechanisms that occur in lithium-ion batteries, which is the part that I'm focusing on. So I think you all understood that my work focuses on the study of lithium-ion batteries, which are nowadays used in most portable applications, and especially electric vehicles. And this is due to their very high specific energy density, which make them a lot more efficient and lighter than any other battery chemistry. So they are very powerful batteries, but they suffer from several drawbacks, and the major one is that their storage capacity decreases throughout their life, and another one is that they have a limited driving range. It's still the most expensive component in an electric vehicle, and its production entails some environmental and human issues. So it is very important to design a strategy that makes it possible for the battery to last as long as possible. So my PhD in this article deals with the design of a prognostics and health management strategy, which aims at predicting the evolution of the state of health of the battery and its remaining useful life. So the state of health of a battery represents its storage capacity at any moment compared to its initial storage capacity, so that's the state of health of the battery. And the remaining useful life of the battery represents the number of charge and discharge cycles it can go through before reaching its end-of-life criterion. So the end-of-life criterion for a battery corresponds to reaching 80% of its initial capacity. So in an electric vehicle, that's the end-of-life of the battery. So we are working on different maintenance strategies, and we have decided to focus specifically on predictive maintenance, which is a type of maintenance that has been developed in correlation with Industry 4.0, and it consists in observing operating data coming from batteries and turning them into a black box model, which makes it possible to forecast the evolution of state of health or to predict the remaining useful life of batteries. So we are using operating batteries in order to predict the remaining useful life, and still keeping in mind this 20% capacity fade end-of-life criterion. So there are two types of remaining useful life predicting models in the literature. And the first one is called I call it the early cycle method, and the second one is called the online window-based method. So the first, the early cycle prediction consists in observing the first charge and discharge cycle, so up to cycle 100. And from this, by comparing cycle 100 and cycle 1, we can compute aging parameters that gives information about the aging mechanisms that are already occurring in the battery. And from these different parameters that are computed from state of health curves, but also internal resistance or any other different curves, we can make a regression on the number of charge and discharge cycle it will go through before reaching its end of life. So it's a global prediction on the global cycle life of the battery. And the second strategy, the window-based prediction, focuses this time on not only the first charge and discharge cycles, but rather a window of charge and discharge cycle. It can be at the beginning, but at any moment of the life of the battery. And by studying this historical window and using recurrent neural networks most of the time, because they are particularly adapted to the study of time series, well, we can focus on a training window and then forecast the future evolution of state of health, and that gives us access to the remaining useful life of the battery in terms of cycle. So in this study, we have decided to make a mix of these two approaches, because we're not predicting the future trend of state of health, but we're rather making a regression on the remaining useful life, but by focusing on a window of data. So we're making a regression on the remaining useful life by focusing on a window of data. So the second step, the second part of the presentation consists in describing the battery aging dataset on which we have based our work on, because when dealing with data-driven strategies, the most important part is to have reliable data. So we have decided to base our work on a dataset that was published by the MIT in 2019, and which is, to our knowledge, the largest publicly available dataset on lithium-ion battery aging. So it gathers data from 124 different battery cells that were tested from beginning to end of life with a fast charging policy, which is really interesting. And this dataset contains two different kinds of information. So first of all, we have different batteries that are tested, and for each cycle of each battery, we have access to summary historical per cycle data. So for example, for each cycle, we have access to one value of internal resistance, average temperature, charge time, etc. So you have one value for each charge and discharge cycle. And then on another scale, we have access to the temporal evolution for each cycle of different values, such as the current, voltage, temperature. So this time it evolves according to the time for each cycle and not according to the number of cycles. So here I have represented the two different kinds of values. So here I have represented the global evolution of external temperature, so it evolves according to the number of cycles. Or here you can see the global evolution of state of health according to the number of cycles. And here, on the other hand, you can see the temporal evolution of external temperature for one charge cycle. So most of the time, window-based strategies, they only focus on state of health curve, so they focus on the sample of state of health to forecast the rest of the curve. But we decided to base our study on historical values, such as state of health and internal resistance, but also on temporal curves of current, voltage, and temperature. So we're focusing on, as I said, current, voltage, and also temperature, which I didn't represent here, for discharge and charge. And we have extracted features from this curve, such as the root mean squared value, the area under the curve, the fundamental frequency, in order to be able to use this temporal series at the same scale of historical values or historical data in our model. So we believe that by using the information that is contained in this temporal series, we can have a more reliable data because they represent the way that the battery is used inside a vehicle, like the driving profile inside a vehicle. So our training dataset is built as follows. We use, first of all, historical data, so state of health, internal resistance, as I said, and then we take advantage of the temporal curves, and we extract features from them, and then we have features that are represented on the same scale as historical data. So our training dataset is built as follows. As I said, we're working on a cycle-based approach, which means that each sample of our dataset corresponds to one charge and discharge cycle, and the target of our network is the remaining useful life of the battery in terms of cycle. So our predictive model is based on a well-known model in machine learning, which is a neural network, an artificial neural network. So our architecture is built as follows. So each sample in our dataset corresponds to, each cycle corresponds to one input sample. So it's a combination of historical features and time series features. And the network is composed by several fully connected layers of neurons, and the output of the network is composed of one single neuron without activation function, because we're making a regression on the number of charge and discharge cycle. So this is the architecture of our model. And here I have represented the predicting performances of our model. So in order to compare the performances of our network, I have built two different artificial neural networks, actually, and the first one only take as input historical features, so internal resistance, charge time, and state of health, and the second one takes the same features plus the time series features that were extracted from current, voltage, and temperature features. So the most important error measurement which is to observe is the mean absolute error. And here we can see that we have a mean average error of 11 cycles, which is quite performing if we consider that on average batteries have a cycle life of about 1,000 cycles, so we have an error which is very low when coming to predicting the remaining useful life. And what's interesting is that we have pretty good results in comparison with other approaches in the literature, because here with our time series featured artificial neural networks, we managed to get an error of about 11 cycles compared to other approaches in the literature that use convolutional neural networks, for example here, which have an error which is 10 times higher. So it's quite encouraging results for this article. So I think it's time to conclude, and well, a brief conclusion would be to say that with the study we have seen that it is really important to design an efficient prognostic and health management strategy for lithium-ion batteries, and that the dataset that we have based our work on is really helpful because it contains a lot of information that is valuable inside our predictive models. And the next step for our work is to go on with the exploitation of time series, current, voltage, and temperature, but this time we want to use more complex neural networks, such as recurrent neural networks, and both forecast the remaining useful life and the state of health of the battery. So that's all for me, and thank you very much for your attention.